Section 14.1 Functions of Several Variables. In real life, functions are not single variable. Most of the functions that you and I would deal with on a daily basis, they are functions of multivariables, such as the temperature on a metal on the floor could be a function of the position where you put your finger on the hot metal. Let's say you have a hot rod or metal on the floor, sitting on the floor, and you want to touch your the metal at different points on the metal or the hot rod. So the temperature will be a function of x and y. The formula for volume of computing the volume of a cone is a function of radius and height. In other words, volume is a function of radius and height. So this is a multivariable function. So what's the temperature? In business field, we have a function called production function, which is a function of L and K, where L is labor, K is the capital, and this is how the formula looks like. This is what business majors deal with it more often in courses like business calculus. So we also have an example of windshield index, which is a function of the actual temperature and the speed of the wind. So notice multivariable functions, they show up in real life. So it'd be nice to examine these kind of functions and learn about their properties and domain and their graphs and their applications in real life. So to begin with, let's define a function of two variables, namely the independent variables are x and y. The dependent variable is z. The formal definition is a mapping. Mapping means it's a rule that assigns each order pair x and y in the domain a unique real number denoted by z. In other words, this is how the function looks like. Z is just a nickname for fxy. So if this is the domain, which happens to be on the floor, it's on xy plane. So for every point here, there is a unique value on this number line, which happens to be the domain of happens to be the value of the function. So this is called the range of the function, which happens to be possible values of z corresponding to the domain which you select on the x and y axis. Once again, for every order pair for functions of two variables, f of x, y, there is a one of a kind, a unique real number on a number line, which happens to be called the range of the function of two variables. So with that said, now let's take a look at this example right over here. See how do we go about doing this. Notice this guy is f of xy is equal to natural log of quantity xy minus 1. Keep in mind z is the same as fxy. So remember, whenever you say f of x and y, that's just a nickname for z, correct? What is evaluate or find f of 1, 1? So that means replace the x's with 1, y's with 1 here. So that would be 1 times 1, which is 1. And let's say this guy is, let's see now, let's say this is, let's say, let's see now. Suppose this guy is just plus 2, suppose. So that would be natural log of 1 times 1 plus 2. That would give you natural log of 3. So therefore, natural log of 3 happens to be what? Is the value of f of 1, 1. When you replace this guy with 1, that guy with 1, 1 times 1 is 1, 1 plus 2 is 3. So notice we get a real number. Do you all see it? On the other hand, if let's say, I don't know, x is equal to e and y is equal to 1, so what do we get? We get e plus what? 2. So that would be like, a real number as well. So that would be natural log of e plus 2. In other words, for every ordered pair, I'm coming up with what? With a real number. I apologize for the example. So it's supposed to be this guy right here. I apologize. So there you go. So that's pretty much how you evaluate. Replace the x with whatever is given, y with whatever is given. So you find this value. Incidentally, this is the value of z. So is here. Do you all see it? So the question is, how do you find the domain of functions of several variables? Well, to begin with, let's review how did we find the domain of what? Single variables, one variable. Okay. Let's say you had y is equal to natural log of x, so you like to know what's the domain of this guy. The domain is all real numbers such that x is greater than 0. Notice I have what? I happen to be shown what? The domain on a number line because I'm dealing with all real numbers. Do you see it? This is when you have a function of single variable. The minute you switch to function of what? Several variables, like let's say 2 variables, now all of a sudden you are on the what? On the xy plane, right? You are on the floor now. You are on xy plane. For instance, suppose I change y equals natural log of x to y equals natural log of x minus y. What would be the domain? The domain is no longer x. Notice is ordered pairs. Do you see it? It's no longer what? X anymore. Do you see it? It's a bunch of ordered pairs such that x minus y is greater than 0. When you say x minus y is greater than 0, that implies y is less than what? X. So what you do, you draw this line, which is y is equal to x. Remember, you cannot be on the line. There is no equal sign. And if you choose a test point like, say, 1, 0, it comes up true, so therefore you have to shade. So you need to come up with a curve and shade the proper region when you're dealing with what? Function of 2 variables. That's what this is called, because you have 2 independent variables. This guy is dependent. So remember, these are independent variables. And this guy is what? Dependent variable. What if I have a function of 3 variables? So you got 3 variables and what? 1 dependent. For instance, what if w is equal to square root of 25 minus x squared minus y squared minus z squared? The domain, now it's not an ordered pair, but it's what? It's ordered what now? Triple. Do you see it? Depending on the number of variables, are they you have what? Real numbers, or you have ordered pairs, or you have ordered triples. In this case, this is a function of 3 variables. So I have ordered triples. So you would say all values of x, y, z such that this radicand, which is 25 minus what? X squared minus y squared minus z squared, has to be greater than or equal to 0, just like for single variables. However, if you simplify and manipulate this, you get x squared plus y squared plus z squared less than or equal to 25. So that means the domain is all ordered pairs either on the boundaries of the so-called sphere or inside the sphere, because you have less than or equal to 25. So you are either on the sphere or you are inside the sphere. Those are the permissible values of x and y and z, which makes up the domain of this function w, which is a function of what? 3 variables. Okay, then we have something called level curves, or also known as contour maps. Basically, level curves of a function of two variables are curves. So these are a bunch of curves such that what? Um, f of xy is equal to constant. In other words, if you replace z in what? In this kind of functions of two variables with a constant. So, and you graph these curves, the result is called level curves, also known as contour maps. So let's see an example of it. Suppose, before we do an example, let me just elaborate. So this means level curves possess what? All points in the domain of fxy, a bunch of order pairs, such that fxy or z is what? Constant. In other words, geometrically it means the surface, z is equal to fxy, is cut by horizontal planes, and the intersection of these two surfaces, namely horizontal planes and the original surface, when it's projected on the what? X and Y plane, those are called what? Level curves. In other words, they all have, in real life, this would be like, they all have fixed what? Heights. Do you see it? So now, let's take a look at an example, then I'll show you where the level curves are used. I'm sure you know it. I just want to kind of reiterate where it's used. Suppose the question is draw a contour map or level curves for z, or which is the same as fxy equals x squared plus y squared. So what do? We let z equal to k, where k is what? Constant, correct? Then we what? Give a variety of values for k. I can't set k equal to negative number because I'm dealing with sum of two squares. So I'm going to choose convenient numbers like 0, 1, 4, 9. When I do, I get this equation, which is its graph is a point. This guy is a circle with what? Radius 1, center at 0, 0. This guy is also a circle with radius 2, center at 0, 0. This guy is circle with radius what? 3, what? Center at 0, 0. So if you would graph this, these are called level curves. Do you see it? Or we can also call this what? Contour map for what? For, what was it? Z is equal to x squared plus y squared. So this is how the contour map looks like. So how did these circles come about? Well, remember the graph of z equals, what was it? X squared plus y squared is called circular, what? Paraboloid. Paraboloid. So when you say k is equal to 0, which means like you're setting z is equal to 0, here you're setting z is equal to 1, here you're setting z is equal to 4, here you're setting z is equal to 9. Z is equal to 0 is just a plane which what? It's along the what? Coordinate system. So the intersection of this plane and the what? Surface is point, as you can tell. When you say z is equal to 1, this is a plane, correct? So when this plane, horizontal plane, intersects what? Circular paraboloid, notice the intersection will be a circle. Do you see it? That's what that is, a circle. Do you see it? With radius 1. The intersection of what? The plane, what? Z is equal to 4, and the surface z is equal to x squared plus y squared is this guy, which is also a circle, right? Can you all see it? And the radius is what? 2. So that's how these what? Level curves come about, by intersecting the surface with bunch of horizontal planes, which these planes happens to be parallel to the what? Floor, x and y axis. So here are 3 examples which I came up with. And this is basically what I have here. One of them is topographical map. So those are like associated with what? The map of the mountains, okay, such that the map like shown below, let me just kind of zoom here so you guys can see how topographic looks like. And basically, these level curves are what? Curves of constant elevation above the sea level. So any of these curves happens to be at a certain what? Height from the sea level. Do you see it? So in other words, if you walk on any of these what? Level curves, you are neither ascending nor descending. You are just what? Walking around the what? Mountain range at a specific height from the sea level. The other application is what? So-called isothermal. Iso means the same. Thermal means temperature. So this level curves shows them what? The isothermal map, which is the level curves. And basically, if you follow any of these curves, notice from, let's say, west to east, notice like on this particular line, the temperature is 20 degrees Fahrenheit from here, from left to right. So any city or country or state, which happens to be right about here, they all have like what? Temperature of 20 degrees Fahrenheit at a specific time of the day. Okay, the final example is called what? Electric potential function, which happens to be a function of x and point x and y. So if you set this guy equal to a constant and draw some curves, those curves are called equipotential curves. That means at any point you select on those curves, what? The potential, electric potential happens to be the same, which is identical. Thank you.